Okay, so we're back with lecture 20, and we are wrapping up chapter 9 today, talking about solution concentrations, the ways that we measure them and how we can use them to do different calculations that we're going to need to, both in the chemistry lab and then in real world as well. So for example, if we were going to make a solution in lab, this is the type of glassware that we would use. This is what's called a volumetric flask. Now, it doesn't look like it measures much, but it measures exactly one thing very well, which is that it measures precisely 250.0 milliliters when you fill up to the one marked line that it has here. So if you were going to make a solution with 250 milliliters, you would put, whatever solute you is. This is 5.0 grams of potassium iodide, but you could use anything. Then you add in the water, dissolve it as much as you need to, and then finally fill it up to that one mark. And that gives you a very precise measurement of the liquid. Okay, so solution concentration can be expressed in a number of different ways, and these are all going to come up. So we're going to learn each of them. Always, though, it takes the general form of an amount of solute divided by a certain amount of solution. Whether that's mass percent, that's a mass divided by a mass. Then there's a volume percent, which is a volume solute divided by a volume solution. There's mass volume, which is mass of solute divided by volume of solution. This comes up actually frequently when you're talking about different IV solutions in your clinic. And then finally, molarity, which is the moles of solute per liters of solution. So we're going to start with mass percent, which is described as M over M. Again, that's just mass of solute per mass of solution. The way that you can calculate the mass percent of a solution is that you take the grams of the solute and divide it by the total grams of solution. Now remember, a solution is a solute plus a solvent. So you take the grams of the solute plus the grams of the solvent. That's your denominator. Divide the grams of solute by that total grams of solution. Multiply it by 100%. Boom, that's your mass percent. Now, the other way that you can think about it is it's also the grams of solute that are in 100 grams of solution. And this is going to be more relevant to us when we're talking about the solutions that we'll be using in class. So let's say that you wanted to make a 16.0% mass over mass solution of potassium chloride. Well, if you take 8.00 grams of potassium chloride, then add enough water to dissolve it in 50.00 grams of solution. Well, that's 8 divided by 50 times 100, which is 16.0% mass over mass solution. So to calculate mass percent, once again, the way this works is you have your grams of solute. That's always going to be your numerator. Then you have your grams of solution, which is both, in this case, the potassium chloride and the water. So 8.00 grams of the KCl plus 42.00 grams of the water gives you a total solution mass of 50.00 grams. Okay, so let's go ahead and give a try at this. Go ahead. This is a relevant sample exercise. I feel like you could probably do this math now if you're ready for it. A solution is prepared by mixing 15.0 grams of sodium carbonate and 205 grams of water. Calculate the mass percent, that's M over M, of the solution. So think it through, try to think it over, and we're going to look at this here in just a minute. So pause the video. Okay, and we're back. So what we have is we have 15.0 grams of our solute, which is sodium carbonate. We have 235 grams of our solvent, which is our water. Remember, the mass percent is the mass of solute divided by the mass of solution times 100%. Well, the grams of solute, that's given to us. It's 15.0 grams of sodium carbonate. We know that the mass of the solution is going to be the mass of the solute plus the mass of the solvent all together. Taken all together, that gives us. So when we look at the math, again, it's 15 divided by 15.0 plus 235, so 250 times 100, that's 6.00% sodium carbonate for a solution. Now, a volume percent might be more useful if our solute is a liquid. So what this is going to be is it's the milliliters of solute divided by the total milliliters of solution times 100%. Again, the volume over volume tells us we have volume in the numerator, volume in the denominator. And again, just like with the mass percent, it's volume of the solute divided by volume of the solution. Now, the way that it's going to be more useful in converting is as a conversion factor, a volume percent will tell you the milliliters of solute per 100 milliliters of solution. Now, combining that, we also have mass volume percent, which is useful in certain contexts. And, sometimes some places just like to have a mass over volume percent. This is what we call the M over V percent. And that's the grams of solute per milliliters of total solution. I can't think of a particular context. Again, for like volume percent, it's pretty clear. Like this is, for example, when you're purchasing alcohol, like, if it's 40% alcohol, that means that there's 40 milliliters of ethanol for every 100 milliliters of the alcohol. Mass over volume percent is a little more rare to see, but there's certain, I know like literally medical solutions will use the mass over volume percent, perhaps because it's just the easiest thing to measure. That could be the case. Okay, so give me two conversion factors for each of these based on what we talked about. Oh, mass over volume here. Again, it's the grams of solute per milliliters of total solution times 100%. And then the conversion factor that you would get is that for each mass over volume percent, that's the number of grams of solute per 100 milliliters of solution. So the first thing we want to learn is what conversion factors can we do for this? Well, I'll help you with it here. For A, 8.50% mass over mass of sodium hydroxide means that we have 8.50 grams of sodium hydroxide for every 100 grams of solution. Or think about it the other way, it's 100 grams of solution for every 8.50 grams of sodium hydroxide. So go ahead and pause the video now, try to come up with the two conversion factors for B and C, and then we'll take a look at the answers when we come back. So go ahead and pause. Okay, we're back. So just like I said, 8.50 grams of sodium hydroxide for every 100 grams of solution, or the reverse of that, the inverse, 100 grams for every 8.50 grams of sodium hydroxide. You have a 5.75% solution of ethanol. That's 5.75 milliliters of ethanol per 100 milliliters of solution, or 100 milliliters of solution for every 5.75 milliliters of ethanol. And then finally, 4.8% hydrochloric acid, that'd be 4.8 grams of hydrochloric acid for every 100 milliliters solution, or the inverse. And then finally, we have molarity. Now, molarity doesn't really show up much outside of the chemistry lab, but it's very useful inside the chemistry lab. So that's why we teach it as one of the important concentrations here within the context of a chemistry class. And molarity is always the moles of solute per volume in liters of solution. So it's always this, it's the moles of solute divided by the liters of solution. So if you took a mole of sodium chloride and dissolved it in 1.00 liter of water, well, you would have a 1.0 molar solution. And sorry, that's one of the ways that we say this. If we have a 1.0 capital M solution, that means it's a solution that is 1.0 molarity. And the way we say it kind of in common words is 1.0 molar. So you'll hear that a lot this semester. Okay, so let's go ahead and look at a molarity calculation, because we're going to use it a lot the rest of the semester. So we may as well get comfortable with calculations with it right now. So what is the molarity of 0.500 liters of sodium hydroxide solution if it contains 6.00 grams of sodium hydroxide? Well, what do we need to know to calculate the molarity? We know that the molarity is the moles of solute divided by the liters of solution. Well, we're given the liters of a solution, right? It says 0.500 liters of solution. The moles of solute, are we given that? Well, no, but we are given the grams, right? So using the molar mass, we can convert from grams of sodium hydroxide to moles of sodium hydroxide. Sodium hydroxide has a very convenient molar mass of 40.00, giving us 0.150 moles of sodium hydroxide. Now it's 0.150 moles of sodium hydroxide for every 0.500 liters of solution, giving us a final answer of 0.300 molar sodium hydroxide. Okay, now why don't you give it a shot? What is the molarity of 0.225 liters of a potassium nitrate solution that contains 34.8 grams of potassium nitrate? Go ahead, pause the video. Remember, what is molarity calculated from, and how can you find those two components given the information that you have here? Pause the video. Okay, and we're back. So the way that we calculated it again is we need the moles of solute and the liters of solution. This time we're given the liters of solution, 0.225 liters of solution. The moles of solute, well, we're given the mass of the solute, that's 34.8 grams of potassium nitrate. So we can convert 34.8 grams of potassium nitrate into moles of potassium nitrate using its molar mass, 101.11 grams. That gives us 0.344 moles of potassium nitrate. Okay, so now we have the moles of solute, we know the liters of solution, so we plug our numbers in, 0.344 moles of potassium nitrate for every 0.225 liters of solution. The answer is 1.53 molar potassium nitrate. So that's how you measure molarity, but the strength of molarity comes from its use as a conversion factor. So if we know that we have a certain molar solution, we can convert between liters or volume of that solution and moles of the solute, which is going to come really handy when we do reactions with dissolved particles. So for example, 3.5 molar hydrochloric acid means that 1 liter of solution equals 3.5 moles of hydrochloric acid. So we have two separate conversion factors we can write. There's 3.5 moles of HCl per 1 liter of solution, and there's 1 liter of solution per 3.5 moles of HCl. So that's a really useful conversion factor. And again, we're going to use that throughout the semester. So we want to get comfortable with it right now. Okay, so let's go ahead and give it a shot. How many grams of sodium hydroxide are needed to prepare 75.0 grams of a 14.0% mass over mass sodium hydroxide solution? Use the conversion factor form this time of the mass over mass, and that's what's going to help you out a lot. So check this out, pause the video, and when you come back, we're going to take a look at the answer to the sample exercise. So go ahead, pause. Okay, now we're back. So again, how many grams of sodium hydroxide are needed to prepare 75.0 grams of 14.0% by mass sodium hydroxide solution? Well, 14.0% by mass sodium hydroxide solution, and we're given the fact that we need 75.0 grams of the solution. Well, our conversion factor here is that for every 100 grams of solution, we have 14.0 grams of sodium hydroxide. That's a pretty straightforward conversion. 75.0 grams of solution times our 14.0 grams of sodium hydroxide divided by 100 grams of solution. That gives us our final answer here, 10.5 grams of sodium hydroxide. Again, we can easily use this as a conversion factor. Okay, how about next? Sample exercise 14. How many milliliters of a 5.75% by volume ethanol solution can be prepared from 2.25 milliliters of ethanol? So again, think about what kind of conversion factor you can get from 5.75% by volume for a solution, and then use that to figure out the milliliters of solution that can be prepared from 2.25 milliliters of pure ethanol. Pause the video, and when you come back, we'll have the answer. So pause. Okay, we're back. So if we're given the fact that it's 2.25 milliliters of pure ethanol, and we have a 5.75% solution that we're trying to make by volume, well, 5.75% by volume means that there's 5.75 milliliters of ethanol for every 100 milliliters of solution. Vice versa, 100 milliliters of a solution for every 5.75 milliliters of ethanol. So our conversion factor looks like this. We have 2.25 milliliters of ethanol. We can make 100 milliliters of solution for every 5.75 milliliters of ethanol, giving us a final answer of 39.1 milliliters of solution. Okay, finally, we're at the big one here, molarity. How many grams of aluminum chloride are needed to prepare 125 milliliters of a 0.150 molar solution? This is a big one. So I know we didn't talk about exactly how to do this, but try to think how to use molarity as a conversion factor to figure out the grams of aluminum chloride that are going to be used to prepare this solution. Hint, what you're going to want to start with your volume. Once you start with your volume, then use the molarity as a conversion factor. And think if there's any way that you can convert from moles to grams. Is there anything that comes to mind as a way to figure out the number of grams of aluminum chloride? Go ahead, pause the video, give it a shot, And when we come back, we'll have the answer. So pause. Okay, we're back. So the big thing here is if we use the molarity to convert from our milliliters of solution to moles of solute, then we can use the molar mass to convert from the moles of solute to the grams of solute. Now, 125 milliliters, we can do the conversion. It's 1 liter per 1,000 milliliters. So it's 0.125 liters. Now, a 0.150 molar solution means that there's 0.150 moles of AlCO3 per 1 liter of solution. And if we find the molar mass for aluminum chloride, that's 133.33 grams per mole of aluminum chloride. So those are our two conversion factors. We have 0.125 liters of solution. We know that there's 0.150 moles of aluminum chloride for every 1 liter of solution. Liters of solution cancel out. It's then 133.33 grams of aluminum chloride per 1 mole of aluminum chloride. Moles of aluminum chloride cancel out. There's our answer, 2.50 grams of aluminum chloride. Okay, so those are our concentrations, and those are the ones that we're going to use a lot this semester. Now, for solutions, there's a lot of things that we're already familiar with and a lot of words that we've used before. For example, dilution. When we make a dilution, it's when we take a solution and add in more solvent. And all that does is decrease the concentration of the solution. So when we dilute stuff, we add water, and then the volume of the solution increases. Because the volume of the solution increases, the concentration decreases. Keep in mind the mass of the solute in the solution will remain the same. Now, the relationship between the initial and final concentrations works like this. The initial concentration times the initial volume is equal to the final concentration times the final volume. And this is true for any concentration and any volume unit. So whether you're using mass percent or molarity, and whether you're using milliliters or liters or gallons, for all I care, this works exactly the same way. Okay, so let's do an example problem using this, this equation. What is the final concentration when 0.50 liters of a 6.0 molar HCl solution is diluted to a final volume of 1.0 liters? Well, what are we given here? Our initial concentration was 6.0 molar, and our initial volume was 0.50 liters. Okay, that's great. Now, our final volume is 1.0 liters. All that we need to calculate for is the final concentration, C2. So if we solve for C2, we find that C2 equals C1 times V1 divided by V2. So just set that up. 6.0 molar times 0.50 liters divided by 1.0 liters means it's 3.0 molar HCl. Now, why don't you give it a shot? And again, you can use any concentration and any volume units that you want for this equation. They all work. What volume of a 2.00% mass over volume HCl solution can be prepared by diluting 25.0 milliliters of a 14.0% mass over volume HCl solution? Give it a try. And if it's still not making sense, we're going to come back at it here once we come back from break. But pause the video now and see if you can come up with the answer. So give it a pause. Okay, and we're back. Now, in this case, our concentration is percent mass over volume, but that doesn't change it. We're still just going to plug in C1, our initial concentration. That's the bigger one here, 14.0%. C2, 2.00%. Again, it's the same, as long as it's the same concentration unit, it doesn't matter which one you choose. And finally, V1 is 25.0 milliliters. So the question is, what is the final volume going to be? Well, if we solve for V2, it ends up being V1 times C1 divided by C2, which is 25.0 times 14.0 divided by 2.00. And that gives us a final answer to three significant figures of 175 milliliters of solution. Okay, now you try this. What is the percent of a solution prepared by diluting 10.0 milliliters of 9.0% sodium hydroxide to 60.0 milliliters? Go ahead, pause the video here. And when we come back, we'll look at the answer. Pause. Okay, and we're back. So what's the percent mass over volume for this solution? Well, what are we given? We have starting from 10.0 milliliters, so that's V1. Then we are diluting at 9.00% mass over volume sodium hydroxide, that's C1, to 60.0 milliliters, that's V2. So the only thing that we're looking for is C2. So once we solve for C2 again, that's C1 times V1 divided by V2, plug in the numbers that we found, it ends up 9.00% times 10.0 milliliters divided by 60.0 milliliters, gives us a final concentration of 1.50% mass over volume. Okay, one more. What is the molarity of a solution prepared by diluting 0.180 liters of 0.600 molar nitric acid to 0.540 liters? Go ahead, pause the video one more time. Use that equation, C1V1 equals C2 times V2, and see if you can come up with the answer. Pause. Okay, we're back. Well, once again, we are given the initial concentration, 0.600 moles. We're given the initial volume, 0.180 liters, and we're given the final volume, 0.540 liters. So the only thing that we're looking for is the final concentration, or C2. Well, if we rearrange our equation, C1V1 equals C2V2, we end up with C2 equals C1 times V1 over V2. So 0.600 molar times 0.180 liters divided by 0.540 liters gives us 0.200 molar solution. Not too bad, right? Okay, next up, we're going to talk about the properties of these solutions and why it is that, the relative percent can be, either life-saving or fatal, depending on what we're talking about. Now, if you ever have worked in a hospital, you've probably seen these drips here, the 0.9% saline drips. And the reason that 0.9% is so important as a saline solution or a salt solution is because it is what we call isotonic with the concentration of solute in your blood cells. Okay, so solutions, they are transparent. They do not separate. So if you leave them sitting out, you're not going to see solids settle to the bottom. And they contain very small particles, which are ions or molecules, that cannot be filtered or pass through semi-permeable membranes. So the only type of things that can be in there are these ions and particles or molecules that they can be then separated out. Colloids have medium-sized particles. They cannot be filtered. In other words, the particles would pass right through. You can use semi-permeable membranes to filter them. And colloids are basically like a substance that's dispersed in another medium just to give an idea. So like fogs, smoke, shaving cream, styrofoam or marshmallows, mayonnaise, cheese, and blood plasma are all examples of different types of colloids. So fog, for example, is liquid water that's dispersed in air. So it's a liquid dispersed in a gas. Smoke, for example, is a solid that's dispersed in a gas. Now that smoke can be filtered out, but it won't necessarily settle easily on its own. I mean, it's still obviously smoke is an entity, right, that you have to deal with. Dust is present, no matter what. So that's why we care about it, is because these things exist, right? Whipped cream is an example of air that's dispersed in a liquid dairy, basically. And that's that type of colloid. Marshmallows have gases dispersed in solids. Styrofoam you can actually see a little bit better. There's chunks of air basically that is dispersed in the styrofoam. Mayonnaise or homogenized milk has liquid dispersed in liquid. So homogenized milk means that it's milk that doesn't settle out. If you get milk straight from the cow, it will just, you'll have the separation of layers of it. You'll have creams and then whatever's below the cream. I can't remember what it's called. The same idea is there. Butter is similar, where it's liquid dairy dispersed in a solid medium. And then finally, blood is another good example of a colloid, where you have solids that are dispersed into a liquid. You have blood plasma as your liquid, and then blood cells would settle out if they were allowed to. So those are colloids. Now, they differ from suspensions in certain ways. Suspensions are heterogeneous and non-uniform mixtures, and they have very large particles that settle out of solution. So I actually told you wrong here. This the particles in blood plasma do not settle out of solution. I was getting ahead of myself there. The solid particles are the platelets that are in your blood. So blood plasma is an example of a colloid because it has small particles that are dispersed throughout. But blood itself is actually a suspension. In order for a suspension to stay suspended, it needs to be stirred constantly. And yeah, so for example, you have blood platelets, muddy water, calamine lotion. I guess I'm not really familiar with that one. But any kind of suspension, you need to constantly stir it to keep it in suspension. So here's our kind of guides to solutions versus colloids versus suspensions. Solutions have very small particles where those particles don't settle, and then they can be separated not by filters, and usually they can't be separated by semi-permeable membranes. Although I think there are exceptions to that. Colloids have larger molecules, but the particles don't settle; they stay suspended in the colloid, and they can be separated by semi-permeable membranes, but not usually by filters. Now, there's some exceptions to that as well. Like good filters can get rid of smoke, for example, or dust from the air. And then finally, suspensions include very large particles that may even be visible, and those particles settle rapidly from those suspensions. So yeah, so that's how we kind of try to keep track of our suspensions, colloids, and solutions. So let's go ahead and do a quick learning check here. A mixture that has solute particles that do not settle out, but are too large to pass through a semi-permeable membrane is called a solution. Is it a colloid or a suspension? Well, that means it is a colloid. So it's solute particles that are too large to pass through a semi-permeable membrane and don't settle out, means that it's a colloid. Now, the next thing that we want to talk about is osmosis. In osmosis, this is where water can move from a lower concentration solution to a higher solute concentration solution. And the idea here is that water is always going to work to even out the concentration of whatever solutions are in osmotic contact. And this is an example here of a semi-permeable membrane. Now, the semi-permeable membrane is something like the cell wall, where large particles can't really get through, ionic particles can't really get through, but water molecules can pass freely through the cell wall. Now, osmotic pressure is important is because the pressure, basically osmotic pressure is the pressure that would prevent the flow of additional water into the more concentrated solution. And as the number of dissolved particles increases, the osmotic pressure increases. And this is really important in terms of your cells. So I think, don't we have it in the cells here? Okay, so we're going to talk about it in the cells next. But for now, let's talk about the process of reverse osmosis. If you look at your water bottle, many waters are purified through a process called reverse osmosis. This is where you take a semi-permeable membrane and you apply pressure to water from one side, and you squeeze it out from a more concentrated solution to a less concentrated solution. This is a way that you can trap ions and other particles and only collect water on the other side, or a highly purified water on the other side. Yeah, now sometimes it's used in desalination. That's pretty rare. It's more often used just in water purification from already relatively pure sources. Okay, so now finally, we're going to talk about blood cells in terms of this. Okay, so in an isotonic solution has the same osmotic pressure as body fluids, like in your blood. So when you have your blood cells in an isotonic solution, the red blood cell has its normal shape and then its normal volume. So that's good. Now, when you have a hypotonic solution, that means you have a lower solute concentration than in the red blood cell. And the water is going to flow into the blood cell to try to reduce the concentration inside the blood cell. Now, the problem is that causes the blood cell to swell up, and it can even pop. This is what's called hemolysis in a hypotonic solution. So this is why drinking too much water can actually be fatal if you drink too much water, or especially distilled water. Now, on the other hand, if you get dehydrated, your blood ends up hypertonic. That's where there's a higher solute concentration in your plasma than in your blood cells. And your red blood cells shrink down into this size here, this hypertonic solution. And what you're actually seeing here is like the skeleton parts of your cell, all the different, what is it called? The different structures that hold the cell together. You can actually start to see them poke out of the red blood cell here. Now, in the same way, this is just as dangerous, if not more dangerous, than the hypotonic cell solution. So in a dialysis patient, or in dialysis, what we do is we take the solution. So we take, basically purifying, like, I think it's from the kidneys here. I guess I should say here, but this is like where you can take what should be purified by the kidneys, pass it into a artificial membrane. What happens is urea, from the blood, right? So you can use the blood and pass it through the dialysis machine, and that will remove the waste particles like urea using osmotic pressure, basically. Okay, so, oh shoot, yeah, I guess I should have emphasized here real quick. An isotonic solution is 5.0% mass over volume glucose and 0.90% mass over volume sodium chloride. Okay, so given all of that, which of these are isotonic, hypotonic, or hypertonic? We have 2% sodium chloride, 1% glucose, 0.5% sodium chloride, or 5% glucose. Again, we want to describe it isotonic, that's inline. Hypotonic means lower concentration than the blood. And then finally, hypertonic means higher concentration than your blood cells. So go ahead, give it a shot. Isotonic, hypotonic, or hypertonic solutions. Pause the video. And let's take a look at the answer here. So a 2% sodium chloride concentration is higher concentration than 0.9%, so that's hypertonic. 1% glucose, that's less than 5%, so that's hypotonic. 0.5%, again, less than 0.9% sodium chloride, that's hypotonic. And then finally, 5% glucose is isotonic. Okay, here we go. So when placed in each of the following, indicate whether a red blood cell will either A, not change, B, undergo hemolysis, or C, undergo crenation. So I didn't really say this here. Crenation happens in hypertonic solution. That's this appearance here. Hemolysis, that happens in a hypotonic solution. So basically, again, it's just isotonic, hypotonic, or hypertonic. Give it a shot. Okay, so 5% glucose, that's isotonic, so no change. 1% glucose, that's hypotonic, so you get hemolysis. 0.5% sodium chloride, hypotonic again, hemolysis. And 2% sodium chloride, hypertonic, crenation. Okay, that covers it for this chapter. So we're going to start the acids bases chapter this week as well. But for now, that does it. Until the next lecture is up, I will see you then, and let's get ready. Bye-bye.